So we have discussed what are H parameters. So what are H parameters? H parameters are nothing but the transistor parameters, which will indicate transistor parameters. So the HI is the input impedance of the transistor, and HR will give you the voltage gain of the transistor. 1 by HR is voltage gain. And HF, current gain of the transistor, and H4 is the output admittance of the transistor. And how to draw the H parameter model for CB, CE, and CC. Small signal H parameter model, CB, CE, CC. And next, how to analyze an amplifier. Analyze amplifier using H parameter. How to analyze amplifier using H parameter model. Amplifier, to the amplifier, we connect a source with the input side and a load across the output terminals, then it becomes an amplifier. Now whatever the block I have represented for BJT transistor, it has to be replaced with H parameter model. Replaced with H parameter. So here we have not mentioned the type of the transistor configuration. Hence I have used only the notation HI, HR, HF, and HNR. This analysis is called as the general analysis. So I1, I2, V1, V2.
Ma'am, your voice is too low, ma'am.
One second.
Your voice is not here.
One second. Is it okay now? Yes, is it okay?
Yes, ma'am.
Okay. So this is the general analysis of the amplifier, where the transistor could be in any one of its three configurations: CB, CE, CC. So this analysis is applicable for all the three types of configurations, and that is why we are simply using the notation HI, HR, HF, H0, and we are using I1, I2, V1, V2. Input I1 represents the input port, 2 represents the output. Analysis. In this analysis of the amplifier, the H parameters will denote the H parameters, which are HI. If I take HI will denote the input impedance of the transistor, and input impedance of the amplifier is going to be different from input impedance of the transistor because of the presence of the source and load resistor. Due to the effect of RS and RL, the H parameters, there is a slight difference between the transistor parameters and the amplifier parameters because of the effect of source resistance and load resistance, which are connected externally to the transistor. Therefore, there is a difference between the amplifier parameters and the transistor parameters. So AI represents the amplifier current gain, whereas HF represents the transistor current gain. AV is the voltage gain of the amplifier, is the reverse voltage gain of the transistor. RI, input impedance of the amplifier. HI, input impedance of the transistor. R0, output impedance of the amplifier. Output admittance of the transistor. So here we have to find, now this is an amplifier, we have to find now the what are the parameters of the amplifier, that is what is the voltage gain of the amplifier, what is the current gain of the amplifier, having known the values of H parameters. So by knowing the H parameters of the transistor, finding AI, RI, AV, R0 in terms of H parameters, in terms of transistor parameters, in terms of transistor parameters. So current gain is the output current by input current, and whenever there is a load, always the current flowing through the load will be taken as the output current. So IL by input current I1. And if we observe in the circuit, if this is the load connected, current through RL will be IL, and I2 and IL both are equal but opposite in direction. Therefore, IL will be replaced with minus I2. IL will be replaced with minus I2. And we have direct equation for I2. The second H parameter equation I have directly substituted and divided by I1. So minus HF minus V2. V2 is nothing but the drop across load resistor, output voltage. So IL into RL. So same thing is substituted here. In place of V2, we have substituted IL into RL. So IL by I1 is nothing but current gain. IL by I1 is nothing but the current gain. So taking again I2 by I1 or IL by I1 minus I2 by I1. She has written IL equal to minus I2, but not required. Here itself you can replace it as the current gain AI. In whichever way you do, you will get the same expression. So IL by I1 is nothing but the current gain. So again, we will replace this with current gain. Take all the AI terms to the left hand side. Take AI common, 1 plus H0 into RL. So this is the current gain. So the sequence which we are following is, next is input impedance, input voltage by input current. So here, if this is RS and this is the source, if this is Hi, then I'm defining the input impedance Ri, that the input impedance is seen by looking into these terminals. So if I look into these terminals, the input voltage by input current. So generally input impedance Ri means input voltage by input current. So what is input voltage? Should I take Vs or V1? So I am denoting the input impedance here, which indicates that this is the input impedance seen by looking into the terminals, these two terminals. So if I look into these terminals, the input voltage available across these terminals is V1. Therefore, I have used V1 by input current is I1. So wherever you indicate the input impedance Ri, the voltage across those terminals will become the input voltage. So V1 by I1. Therefore, I have not taken Vs. I have taken V1 by I1. So we have a direct equation 1, H parameter equation 1 for V1. So I have substituted, and if you simplify, you will get Ri. So V2, once again, V2 is nothing but the drop across RL. So IL into RL, again IL by I1 is current again. So like that, if you simplify, you will get the input impedance. And voltage gain, output voltage by input voltage, V2 by V1. So V2 is I drop across RL, and V1, just now I have shown you that if this is HIE, this is V1, and if I look into these two terminals, I've denoted the impedance as Ri, the input impedance is Ri. So we defined input impedance Ri as the input voltage V1 by I1. Now here the input voltage V1 I will write now as Ri into Ii, Ri into I1. So in place of V1, Ri into I1. So like that you will get the voltage gain and output admittance. Finding the output admittance, you need to follow certain steps. First one is, if there is any source is there in the input circuit, make it 0. Make it 0. So the voltage source, there is no voltage source. I have set it to 0. And removing R0, we need to disconnect load resistor. Here across H0, we used to connect a load resistor, but I have disconnected that, and I have applied a voltage source V. After disconnecting load, apply a voltage source V, and let I is the current generated by this voltage source. So V by I is nothing but the output impedance R0 and V by I. So if you observe V, the notation what we are following is that the voltage across H0 is V2. So therefore, V, I am replacing it with V2. And if you see the current direction, the I and I2 both are same. So therefore, I is I2. So V2 by I2 is the output impedance of the amplifier. So we have so instead of finding,
మ్యామ్
yes,
ట్రాన్సిస్టర్ లో అవుట్పుట్ అడ్మిటెన్స్ తీసుకుంటాం కదా మ్యామ్, ఇందులో అవుట్పుట్ అడ్మిటెన్స్ తీసుకోవాలి కదా.
అట్లేం లేదు బాబు.
ఓకే మ్యామ్, అంటే నేను సాలివాహనాలో అవుట్పుట్ అడ్మిటెన్స్ ఉండే మ్యామ్, సో అందుకే డౌట్ వచ్చింది.
ఆహా, లేదు లేదు, అవుట్పుట్ అడ్మిటెన్స్ ఇంపెడెన్స్ క్యాలిక్యులేట్ చేయడానికి ఏమవుతుందంటే, ఇప్పుడు చూడండి V2 by HFI1, this expression will become reverse, right? So simplification is going to be complex. That is the only reason why we are directly finding the admittance. Later inversing that, you will get the impedance. So that is the only reason why they are directly calculating the output admittance.
Okay, ma'am.
So when we are calculating the voltage gain, AV, we have taken the input voltage, output by input. So we have taken input voltage as V1. But practically the voltage gain means the input voltage must be Vs. So V2 by V1, this is the voltage gain. Here, this is the voltage gain, assuming that Rs is 0. We said that V2 by V1, this voltage gain represents that it is the voltage gain with Rs equal to 0. If Rs is 0, suppose if Rs is 0, then whatever is the source voltage, the same voltage will appear at here. V1 and Vs both will be same. If if Rs equal to 0, V1 is equal to Vs, and the voltage gain, this is the voltage gain. So V2 by V1 or V2 by Vs, one and the same. So AV represents the voltage gain with Rs equal to 0. It means it is not considered the effect of Rs. Ideally, Rs is 0. Rs will be 0 only for an ideal voltage source. If the voltage source is ideal, then only the internal source resistance Rs will be 0. So when we have not considered Rs, that is Rs equal to 0, whatever the voltage gain we are calculating, this voltage gain represents the voltage gain of an amplifier when the input voltage source is ideal. But we cannot realize an ideal voltage source, right? Obviously, some internal resistance Rs will be there practically. Therefore, voltage gain of an amplifier means practically this is more meaningful compared with AV. Because practically some internal resistance will be there. Some internal resistance will be there for each voltage source. If I look into these terminals, the input impedance I denoted with is Ri. So the entire input impedance of the circuit I replaced. I replaced this terminals with its input impedance, and the voltage across that is V1 and the current is I1. So AV with Rs into account, then I will take output voltage V2 and input voltage is V1. So V2 I am Vs multiplying and dividing with V1. So V2 by V1 anyhow we know we have already done, and V1 by Vs. So this we have already calculated, which is nothing but the voltage gain with Rs equal to 0, and we want to find the expression for V1 and Vs. So if you apply KVL to this loop, I can write V1 as Vs into Ri by Rs plus Ri. And therefore V1 by Vs is Ri by Rs plus Ri. So this is the practical voltage gain AV into Ri by Ri plus Rs. This is the voltage gain with source resistance taken into account. So in a similar way, you have to find out the current gain. Current gain considering the effect of Rs. So for that, the voltage source must be replaced with its equivalent current source. So I equal to V by Vs by Rs. So this is the current source Vs by Rs, and the internal resistance of the current source comes in parallel. So Rs. By taking the effect of Rs into account, the current gain the definition becomes output current IL by input current IS. So divide and multiply with I1. IL by I1 is current gain. This is the gain with RS equal to 0 and I1 by IS. So apply current division rule. Apply current division rule, you can get this I1 by IS. So power gain is voltage gain multiplied with current gain. This is power gain. So this is the amplifier analysis. And whatever equations we have derived, these are applicable for all the three transistor configurations. So direct to 10 marks, you will be asked to derive all these 7 parameters: AI, AV, RI, R0, AVS, AIS, power gain. So I don't know whether it is there in the syllabus or not, but you have to know that H parameters generally they will be provided by the manufacturer when you buy a transistor. So when you buy a transistor, the H parameters will be provided. Otherwise also you can derive the H parameters from input and output characteristics of the transistor. So even if they are not provided, you can derive the H parameters from the input and output characteristics. If you want H parameters of CB, so from the input and output characteristics, you can get the H parameters of CB. So like that. So how to find the H parameters from the input and output characteristics? So we will see. Let us take so HI. First we will write HI. What is HIB? What is HI? We'll take common base. Base, emitter, collector. Emitter current is the input current. VBE is the input voltage. IC, input output current. VCB, output voltage. So we know HI, first we will write the equations. V1 equal to H1, HI I1 plus HR. We'll write the equations. V1 equal to H11 I1 plus H12 V2 and I2 is equal to H21 I1. Write these equations first. Now I am changing these equations. So in place of H11, so in place of H11, I will write HIB, HRB, H21 means HFB, HOB. Now next, in place of I1, I will remove this 1, 2 subscripts. So I1. So I1 means IE, V2, VCB, IE, VCB. So now HIB, I will write it as, okay, here V1 means VBE, I2 means IC. So HI means V1 by I1 So there V2 they have taken constant, but here 0, but we will take it here constant for a constant value of V2. So VBE by IE with VCB constant, with a constant VCB. This is input impedance. So from the input characteristics, we will see what parameters we can derive from the input characteristics of CB. From the input characteristics of CB. So input characteristics are drawn between the input current IE and input voltage VBE. So let us say that this is the characteristic curve. VCB, some 2 volts. So how to find the input impedance? Input impedance, always the input impedance is all the parameters are by default the dynamic parameters. It means we are going to write delta VBE by delta IE. So with VCB constant, with VCB constant. So generally when we perform the experiment, we'll be performing twice, right? Let us say this is 4 volts, 2 volts. So with VCB constant, it is, the definition is saying that with VCB constant means I am taking this curve. I can take any one curve. I will indicate 2 points. For VCB constant, 2 volts constant curve I am taking. I take 2 points. This will be the IE2, IE1, and this is VBE1 and VBE2. So this difference will give you delta VBE, and this difference will give you delta IE. So like that you can find the H parameter HIB of the common base from the input characteristics. What else we can find from the input characteristics? So 2 parameters can be found from the input and the other 2 can be found from the output. So which 2 can be found from the input characteristics and which 2 can be found from the output characteristics? So this is the one parameter I have shown you how to derive the HI input impedance of the transistor using its characteristics. Now see here, from the same input characteristics, you can also find HRB. You can find HRB. This is not delta. So what is HRB? HRB is nothing but first if you are confused directly writing this equation, first write the basic definition. Reverse voltage transfer ratio V1 by V2 with I1 as constant. So V1 by V2, or else I'll write here itself once again. HRB, HR is V1 by V2 with I1. I1 there it is taken 0, but here we will take it as some constant value other than 0. So V1 is nothing but VBE, V2 is nothing but VCB with IE constant. So in which graph you have input voltage, output voltage, and input current. Which graph consists of these three parameters? Input characteristic, which characteristic curve contains these parameters? Input or output?
Output.
Input characteristics means input current, input voltage, input current, input voltage. Which will be fixed constant? Which will be constant in input characteristics? Yes?
Output voltage.
Output voltage constant. So VCB constant. What about the output characteristics? Output current IC versus output voltage VCB with IE constant. So which characteristic curve involves these three quantities? You tell. Which characteristic curve involves these three quantities? VBE, VCB, IE. Yes, your voice is low, Harshita. It is correct. Input characteristics. See, VBE x-axis, IE y-axis, VCB the constant parameter. So therefore, HRE also can be found from input characteristics. First, you have to identify which two parameters, which parameter is obtained from which characteristic curve. So HI, HR, HI, HR are calculated from input characteristics. H0, HF are calculated from output characteristics. So how can we find this HR? We will see. Let us say this is 2 volts, 4 volts. So IE constant, right? HR, the definition, which is delta VBE, all by default, all are dynamic parameters only. Delta VCB by IE constant. So therefore, what I'm doing, I'm fixing one current constant. I'm taking a constant emitter current. So at this particular constant value of IE, at this constant IE, I will draw a line onto the characteristic curves, so which intersects the two characteristic curves. So the input voltage corresponding to this input current is, this is VBE2 and this is VBE1. So HF, now I will write HRB as delta VBE by delta VCB. Let us say I have taken IE as 2 milliamperes constant. I have taken some value 2 milliamperes. So I'll write IE equal to 2 milliamperes. Now delta VBE, how will you get delta VBE? So VBE1, higher value minus lower value, whether it is 2 or 1, just forget about it. Higher minus lower VBE2 by VCB. VCB is 4 volts minus 2 volts. So VCB, we have taken two set of curves, 2 volts and 4 volts curve. So this 2 and 4, the difference of 2 volts and 4 volts. So this will give you the reverse voltage reverse voltage transfer ratio of common base. So like that, you have to find the H parameters from the input and output. You can also find H parameters from the input and output characteristics of the transistor configuration. If they are not provided, and if you have input and output characteristics with you, you can get them using this procedure. So from the input characteristics, you can find HIB and HRB. So output admittance and forward current gain can be obtained from the output characteristics. So for finding impedances, for finding impedance or admittance, you need only one curve. One curve is needed either for finding the admittance or impedance, whether it is an input impedance or output admittance. One curve is sufficient. So here I have taken one output characteristic curve. One output characteristic curve I have taken. Output admittance is I by V. So output current by output voltage. So delta I by delta V with input current constant. With input current constant. This is the definition, right? H22 is I2 by V2 with I1 constant. So take one output characteristic curve, indicate 2 points. The procedure for finding impedance at admittance is same. Take 2 points on the characteristic curve. These 2 points must be there in the active region, not in the saturation. So take 2 points, indicate the corresponding currents. This is IC2 and this current IC1. Then, so this difference is delta IC and this difference is delta VCB. With IE 2 milliamperes, you can take any value, not necessarily 2. Generally, we put 2, 4, 6 constant in the lab, right? So any value of curve, any curve you can take, 2 milliampere curve or 4 milliampere curve. So this is how you need to find the output admittance. And the last one, forward current gain. So forward current gain, the definition is I2, output current by input current with V2, right? So output current, input current, output voltage. These three things you can see in the output characteristic curves. Therefore, HFE also can be found from output characteristic curve. The way we found for HRE, HR, the same way we need to find HF. For a constant output voltage, so x-axis is output voltage, y-axis is output current. So I'm taking some fixed current. At this particular voltage, I'm finding the current gain. So I'm drawing a line onto the characteristic curves. You can select an output voltage constant in the active region. Draw a line. So let us say 2 volts, VCB 2 volts. And this is intersecting the two characteristic curves. The output current corresponding to this is IC1. The output current corresponding to this point is IC2. This difference will give you the delta IC and this difference will give you delta IE. You can, let us say this is 2 milliamperes, IE equal to 4 milliamperes. So this will give you delta IE. So IC2 by IC1 minus 2 milliamperes. The difference between 2 milli, 4 milli is 2 milliamperes, right? So like that you can find HF from the output characteristics. See, we have the equation V1 equal to HI I1 plus HR V2. So this equation HR, HI both are there. That means you can remember that these two can be found from input characteristics. And from the second equation, I2 equal to HFI1 plus HOV2. So whichever parameters HF and H0 both are there in the second equation. So these two are found from the output characteristics. Like that you can remember. And finding H0, HI, one characteristic curve is sufficient. With one characteristic curve, you can find the impedance or admittance. And for finding HF and HR, you need two set of characteristic curves. Two set of characteristic curves. So now I will ask you people to find the H parameters of CB and CE. We have performed CB and CE characteristics in the lab. So from the graphs, find out the H parameters of CB and find out the H parameters of CE. And you need to write in the result part the H parameters of CB and CE. Calculate in the record the H parameters of CB and CE. So H parameters are fixed. These are fixed for one configuration. And they are going to vary from one configuration to the other configuration because transistor will behave differently. The performance of the transistor is different in each configuration. Therefore, they have a different H parameter values. Now, to compare CB, CE, very important for 4 marks. Compare CB, CE, CC. Compare CB, CE, CC. Very important for 4 to 5 marks. 99% in every question paper this will come. So comparison. So to compare, we will calculate the current gain, input impedance, voltage gain, output impedance of all the three amplifiers. We have the equations for AI, RI, AV, Y not. See here, H parameter values are there. H parameter values of all the three configurations is there. And what else you require to find the amplifier parameters? Other than H parameters, what you need? Can anyone answer? For finding AI, what you require? For finding RI, what you require? For finding Y not, what you need? What data you needed?
RL.
It means for finding this AI, AV, RI, R naught, you need to know the H parameters of the transistor configuration. In addition to that, you should have the values of RS and RL. So RS source resistance, load resistance values both must be provided, and also H parameters of the transistor configuration will be provided to you. You can check in the assignment question. I have given related problem. So H parameters will be provided in the problem. In addition to that, RS and RL also will be provided. This will be given data for the amplifier analysis. For finding the amplifier parameters, this will be given to you. Just substituting these parameters into these equations, you have to find the current gain, voltage gain, input and output impedances. So here, find AI, AV, RI, R0, AIS, EVS, considering that RS is 1K and RL is 3K. RL is 3K. So for AI, for common base, they found that AI is 0.978, and for common input impedance 22.8. Just they have substituted current gain, voltage gain, and output impedance. Similarly, for common emitter, so I have given them exercise to find out using the H parameter values given in the tabular column and considering RS 1K and RL 3 kilo ohm. I asked them to find the AI, RI, AV, A0 for CE amplifier, for CC amplifier. So if the configuration is CC, then these will become the CC amplifier parameters. So in the equations, everywhere you need to replace HFC, HIC, HRC, and HOC. Equation is same. Only the thing is that this is subscript you are going to change to C. CC means C. Common base means B. And it is again, once again, this they have found these 4 parameters of CE amplifier, CC amplifier, and CB amplifier. So using the H parameters of CE, using H parameters of CE, they calculated these values. The current gain, voltage gain, input and output impedance of CE amplifier. And using the H parameters of CC, they found this current gain, voltage gain, input and output impedance of CC amplifier. Now we can write here, this is the amplifier. Amplifier, AI, AV, RI, R0 are the amplifiers, right? So CE amplifier. CB amplifier. So if you observe, these values are obtained by substituting the H parameters of CE into these equations. From where you got these values means they have substituted the H parameters of each configuration, and RL I also provided. So just substituting the H parameters and source and load resistances, they have calculated the current gain of amplifier, voltage gain, input and output impedances of all the 3 amplifiers. Now, first point, observe here. There is a negative sign. If you observe for CE, there is a negative sign for current gain, voltage gain, and these are positive. Whereas in CB and CE, they are positive values. So positive values, meaning is that AV is negative for CE, meaning is that if you give a input signal, a small weak input signal, 130.97. Let us say I'm taking that value minus 130.97. Okay. So meaning is that AV is output voltage by input voltage is 130. It means output voltage is 130 times the input voltage. Input voltage is amplified by 130 times, increased by 130 times. So the output voltage, this is the output voltage of CE amplifier with a phase reversal of 180 degree. So when input is increasing in the positive direction during the first quarter half cycle, output is decreasing. So minus sign indicates that there is a phase shift of phase difference of 180 between input and output. So this is the first difference between comparison between CB, CE and CC. The first comparison is that when you are comparing AI, AV, RI, R0, in addition to that, add one more row phase shift. Add one more row for phase shift. So 180 degree phase shift, whereas 0 phase shift in CE and CB and CC. That is the first comparison. Second comparison. One 180, 0, 0. This is CE, CC, CB. Next, we will see voltage gain. Voltage gain, if you observe, common collector, voltage gain is just almost 1. So common collector, voltage gain is 1 means what? What do you mean by unity voltage gain? What it indicates? Voltage gain 1 indicates what? Voltage gain is approximately equal to unity. Means there is no amplification, no amplification. So common collector does not amplify a voltage signal. It will not amplify if we give an input signal as the voltage, no amplification. Output voltage, whatever is the output voltage, the same will be the, whatever is the input voltage, the same will be the output voltage. So no amplification. Whereas in CB and CE, if you observe, CB and CE, if this is 127, if this is 127, this is 130. They are almost same. So from this voltage gain, you can compare that. The voltage gain, you can write a comparison statement that voltage gain of CE and CB are approximately equal. Common emitter and common base amplifier provides voltage gain which are almost equal, whereas in CC the voltage gain is approximately equal to unity indicates that there is no voltage amplification in common collector. So that is another comparison. Coming to the current gain. If you observe current gain, see here, CB. Current gain is approximately 1. So we will write first current gain. If we write current gain, CB, the current gain is almost unity, same. It means no current amplification. No current amplification. No current amplification. So first thing we have observed that common base is giving a unity current gain. It indicates that output current by input current is 1. So output and input both are equal. So whatever input is there, the same will be the output. Whatever input current provide, the same will be the output current. So no current amplification. Coming to the CE and CC, if you observe, for one it is 46 and for one it is 47. So 46 and 47. It means the current gains of CE and CC are almost same. If this is 46, it is 47. You remember, same is followed here also. If beta is the current gain of common emitter, beta plus 1, gamma is the current gain of common collector. So though beta represents the current gain of transistor, but here also we could see that plus 1 difference is getting reflected here also. So from the current gain, you can write a comparison statement that common base provides unity current gain. Common base provides unity current gain. It means there is no current amplification in common base. Whereas in CE and CC, current gain, CE and CC provide current gain much greater than unity, which are almost same. So that is the next comparison statement you can write among the three amplifiers. And coming to the input impedance. See here, input impedance. If you observe, input impedance is very high for common collector. Input impedance is very high for common collector, whereas very low for common base. So input impedance, Ri, if I write, very high, very low, medium. So common collector provides high input impedance among the three configurations, and common base provides lowest input impedance among the three configurations. I can write here instead of very high, highest and lowest. So you can write here the highest among the three, and this is lowest. And the last one is R naught. R naught. Highest is CB, lowest is CC, reverse. So now here it is exactly reversed. It is exactly reversed. See here, output impedance. You can just interchange the CBCC. This is lowest now, highest. And again here this will be medium. This will be medium. So comparison means this is the comparison. The same is written here in the form of statements. So from the table it is observed that CE amplifier is the one. Now you observe this. Observe here. Common collector, no voltage gain, no voltage amplification. Common base, no current amplification. But here in CE, both voltage amplification is there and both current amplification is there. So that is why CE has become more popular over CB and CC, because it can amplify a current signal as well as voltage signal. So that is what here written. Because a high voltage gain is there and as well as high current gain also there. So it provides both voltage and current gains, CE. Therefore, CE amplifier is the most widely used amplifier. And this here it is writing CE. So RI and R0, RI and R0 also, they are medium. Another important aspect of CE is that, another important aspect, CE, if we summarize only CE, voltage gain is much greater than unity and current gain also very, very large. So both current and voltage amplification, both current and voltage amplification. And another point is that Ri and R0 does not vary with Rs, RL. So the meaning is that we have derived the expression for Ri and R0, which might have included the values of either Rs or RL. I will show you just. Okay, I'll write the equation for Ri. What is the equation? We got Hi plus HR into AI into RL. This is the equation. Now, if you look at this equation, Ri, it is a function of load resistor RL. It is a function of load resistor RL. So, the speciality of CE amplifier is that the input, even if you vary RL, Ri is not going to change much. Ri is not going to change much. So that is the benefit. It is given, right, that Ri and R0 of CE amplifier doesn't vary much with Rs and RL. అంటే RSRL వాల్యూస్ RSRL మార్చుతున్నా పెద్ద వేరియేషన్ ఉండదు RI R0లో, ఇంపెడెన్సెస్లో వేరియేషన్ ఉండదు. సో that is also the important benefit of CE amplifier. Even if RL is changing, even if RS is changing, they are not going to vary much. That is the another advantage. And Ri and R0, both are, these two are medium compared with CB and CC. Same thing is written, Ri and R0 lie between those for CB and CC. So therefore, they are called as moderate. And negative sign indicates that there is a phase difference of 180 degree. This is the first, second, and third 180 degree phase shift. Fourth, Ri, R0 lie between that of CB and CC. So coming to the CB, it is identified that current gain of CB is 1. So no current amplification. Alpha 1 kada. Alpha, which is the current gain of transistor. Current gain of transistor is 1 there, and current gain of the amplifier also is 1. CB, if you recollect, the current gain of CB transistor is 1. And current gain of amplifier is also approximately 1. This is amplifier. So no current amplification. Once again, just whatever we compared, here it is written in the form of statements, no current amplification. So based on this point, current amplification em undadu common base lo. It means output current by input current is 1. It means output current is same as input current. Therefore, you can use this common base as a constant current source. You can use common base sometimes as a constant current source because output and input currents are same. The one application of common base is that you can use common base as a constant current source. Current is going to be constant. Whatever input current is there, same current will be flowing in the output circuit as well. So constant current source. And coming to the voltage gain is much greater than unity. So how much it was? It was voltage gain anta CB 127. So voltage gain of CB, it is from the tabular column 127. Okay, so voltage gain, it is positive in CB. So it is not inverting the signal. It is not giving a phase difference of 180. So we say that it can also be called as, non-inverting amplifier. Non-inverting amplifier because it is not inverting the signal. It is not inverting the signal. So 0 degree phase shift. Positive means 0 degree phase shift. So it will not invert the signal. If this is the input signal, if this is the input voltage signal, output voltage signal also will be in phase. Output voltage signal also will be in phase. Hence it is called as non-inverting amplifier. And the fourth one, we can use CB if you see CB, see here CB, Ri is low and R0 only CB, if you see, input impedance is very low and output impedance is very high. That means low input impedance, high output impedance. So because of this low input impedance and high output impedance, CB can be used between two stages. CB can be used between two stages. Say this is load and source. This is a source and this is load. If source impedance is low, if load impedance is high, this CB can be used for impedance matching. Can be used for impedance matching. It can be used for impedance matching between a low impedance source and a high impedance load. Between a low impedance load source and a high impedance load. If there is no matching, generally for to get maximum power transfer, impedance matching must be there. So if there is a mismatch, then the maximum power will not be delivered to the load. Suppose if source is very low, see here, source is low, RS is low, and RL is high. So there is no power, maximum power may not be delivered from source to load because there is a mismatch. Now, what I will do, I will insert in between source and load, I will insert a common base transistor configuration so that the low source impedance will be matched with low input impedance of the amplifier and high load impedance will be matched with high output impedance of the amplifier. So there is a matching low and low so that whatever the power is there that will be delivered to the common base maximum, and since there is a matching between the R0 and RL, the maximum power will be delivered to the load. So like this, CB can be used to provide impedance matching between a low impedance load and a high impedance, between a low impedance source and a high impedance load. So these are the applications of CB. CE, the main application is, it is the most widely used amplifier. This is the application. Whereas CB, it can be used as a constant current source. It can be used for impedance matching, non-inverting amplifier, constant current source. CC, coming to CC, CC reverse. We can remember easily the CC and CB. CC and CB. CBలో కరెంట్ గెయిన్ మీరు గుర్తుపెట్టుకోవచ్చు, ఆల్ఫా కరెంట్ గెయిన్ 1. అంటే CBలో కరెంట్ గెయిన్ ఆఫ్ ది కరెంట్ గెయిన్ is 1, whereas in CC voltage gain is 1. So reverse, you can remember exactly reverse. Current gain is 1 in CB, whereas in CC voltage gain is 1. Voltage gain is 1. అండ్ CBలో RI లోయెస్ట్, R0 హైయెస్ట్ అయితే ఇక్కడ రివర్స్, హైయెస్ట్ లోయెస్ట్. సో అలా గుర్తుపెట్టుకోవచ్చు. సో CC, again CC is also used to provide impedance matching. CC, see here, RI is highest, R0 is lowest. Are they same concept? The only difference is that if RS is high, highest, very high and RL is low, then to provide the matching between RS and RL, I will insert in between the common collector, because the input impedance Ri is high, very high, and R0 is very low. So what this high source impedance and high input impedance, the high source impedance and high input impedance. So this high and high, so RS and RI will be matched. Therefore, maximum power will be delivered to the input terminals of the common collector. Since R0 and RL are matched, low, low, whatever the power has come to CC, the entire power will be delivered to the load. So CC is used to provide impedance matching. It is used, this is also used for impedance matching between high source resistance and low load resistance. And another important, widely used it as a buffer. This is again important. What is buffer? They will ask you in the Viva. So CC, it is used as buffer. Buffer, it is nothing but a storage. So why we have not called common base as buffer? Why we have called only common collector as buffer, CC as buffer? So for the buffer, బఫర్ అనేది ఏంటంటామంటే వోల్టేజ్ గెయిన్ 1 ఉంటే దాన్ని వోల్టేజ్ గెయిన్ 1 ఉండాలి, అండ్ ఎట్ ద సేమ్ టైం వోల్టేజ్ గెయిన్ మస్ట్ బి యూనిటీ, అండ్ ఆల్సో Ri should be very high and R not very low. So this circuit whose voltage gain is 1 and input impedance is very high and output impedance is very low, that is called a buffer. So what that buffer will do? Suppose some 5 volts it is giving, 5 volts it is giving, right? So since input impedance of the CC amplifier is very high, since Ri is very high, whatever 5 volts is there, that entire 5 volts will appear across the terminals of CC. Since Ri input impedance of the CC is very high, whatever the source voltage is there, that entire source voltage will appear at the CC amplifier. So voltage gain is 1, means the output voltage is same as input voltage. So the same 5 volts will be available at the output terminals. Since same 5 volts will be available at the output terminals. So whatever 5, since Ri is very high, very negligible drop will be there across the source resistance Rs. So drop is almost zero, and entire 5 volts will appear at the input terminals of the common collector. So voltage gain is unity, means whatever 5 volts is there at the input terminals, the same 5 volts will appear at the output terminals. And since R0 is very low, negligible drop across R0, and most of the 5 volts will be delivered to the load. Because this R0 and RL is acting like a potential divider network, so this 5 volts should get divided among R0 and RL. But this R0 is very, very low. Therefore, drop across R0 less drop will be across R0, and most of the voltage will be available at RL. So the buffer, what it is doing, it is acting like a storage element. Whatever the information we are giving from the source, the same information will be stored and it will be delivered to the load circuit. So that is called buffer. So in digital circuits, we will use this buffer. So if we want to store a logic 1 or logic 0, so logic 1 means high positive voltage, 0 means 0 volts, like that. So this is the buffer. Buffer is the one whose voltage gain is unity, and input impedance is very high, output impedance is very low. So these are the comparison and applications of CB, CE, very, very important for 5 marks. And coming to the approximate model. So whatever the equations we have derived for AI, whatever equations we derived for current gain of the amplifier, which is minus HF by 1 plus H0 into RL, Ri is equal to Hi plus HR AI into RL, and voltage gain is current gain AI, load resistor RL by Ri. And why not, I didn't remember this equation, H0 minus HR HF by Hi plus, I don't remember this equation. Okay, so these are the equations.
RS
Yes,
plus RS.
is it RS? Okay, so these are the equations we have derived using exact H parameter analysis, using exact H parameter model. So I told you the exact model means it includes all the 4 H parameters. So using exact H parameter model, these are the equations we derived for current gain, voltage gain, input impedance, output impedance. In addition to that, AIS is AV into Ri by Ri plus Rs, and current gain is AI into Rs by Rs plus Ri. So these are the gains, taking the effect of Rs into account. Taking effect of Rs into account. So Rs 0 jaisa, if you set Rs 0, then if Rs equal to 0, then AVS will become AV and AIS will become AI. Okay, so here itself you can try to note that these two equations, these are valid, whether it is calculated using exact model or approximate model. So these equations are valid for both exact and approximate. The basic four equations AI, Ri, AV, Y naught. These are derived using, these are the equations obtained by using exact H parameter model, exact model. Now, we will see what is the approximate model. Approximate model. So approximate model is derived for common emitter, is derived from common emitter amplifier. See what is that. So I'll write first the HIE for common emitter. I will write HRE, VCE, HFE, IB, this is 1 by HOE. So till here, this is the equivalent model of the transistor. This is the equivalent circuit of the transistor, right? So the input current of common emitter is IB, output current is IC, VBE, VCE. So this is base, emitter, collector, emitter. This is the transistor. We have not yet formed the amplifier. Now to form the amplifier, what I am doing, to the right, to the left, that is across the input terminals, I am adding a source. And across the output terminals, I have connected a load. So this current, I am calling it as load current. IC and IL both are same. So IC is equal to minus IL. Magnitude same. IC is equal to minus IL. Okay. Now, generally the RL value will be in the order of tens of kilo ohms. RL 10K, let us say we will take RL 10K. And if you observe from the output circuit, so from the output circuit, how 1 by HOE and RL are connected? How 1 by HOE and RL are connected? Can anyone?
Parallel.
So no one is answering. Always either
Parallel.
70 or 307. Only from these two people I am getting the answers. I don't know what the other people are doing. So if you observe from the output circuit, we have simply connected this HOE parallel. We connected this load resistor across the output terminals. So RL is just connected across the output terminals. That means RL and HOE, they will be in parallel. RL and HOE, 1 by HOE are in parallel. So RL 10K, we will see what is the value of 1 by HOE. What is the value of 1 by HOE from this tabular column? Okay. So see 1 by HOE value is around 40K. Around 40K like that. Okay. So 1 by HOE is 40K. So RL in parallel with 1 by HOE. How much will be you will get? How much you will get? Yes? Yes, sir. So approximately equal to RL. So I'll write a general note that now I will write a general note that if RL is very low in comparison with 1 by HOE, if RL is very low in comparison with 1 by HOE, then if you see the parallel combination of RL and 1 by HOE, then this parallel combination will result into the value which is approximately equal to the lower value. So one is RL is higher and 1 by HOE is RL is low and 1 by HOE is very high. Then the parallel combination of a very low resistor and a very high leads to the value approximately equal to the lower one. So which is equal to 1 by, which is equal to RL. Therefore, the first condition is that if RL is much greater, RL is much smaller than 1 by HOE, RL and 1 by HOE parallel combination approximately equal to RL. Therefore, 1 by HOE can be neglected. So from the circuit, we can neglect one H parameter. Out of the 4, we can neglect one H parameter, 1 by HOE. So 1 by HOE. Therefore, the circuit becomes, see here, therefore, there is no, you can remove this 1 by HOE. You can remove this 1 by HOE. You can neglect this 1 by HOE only when this condition is satisfied. Only when this is satisfied, you can neglect one H parameter 1 by HOE. Okay. So I have removed that 1 by HOE from the circuit. So if I remove, what will be the IC? If I remove, what will be the IC? This is the collector current IC. So what is IC? Can anyone tell? So the current IC is what? Now IC is equal to HFE into IB. Now this HFE into IB will become IC. అంతే కదా దిస్ ఈజ్ ది కలెక్టర్ కరెంట్. ఇంతకుముందు ఇక్కడ రెసిస్టర్ ఉండింది కాబట్టి ఆ కలెక్టర్ కరెంట్ ఇటు డివైడ్ అయింది. when there was a resistance 1 by HOE, the collector current IC after reaching this node, it is getting divided into two components. One is current through this branch, which is HFE into IB, and current through this branch. But here if we have assumed that RL is very low compared with this 1 by HOE, so there is no, this is neglected. So this 1 by HOE is easily neglected. Therefore, whatever collector current is there, that entire collector current now it will flow through this branch only. Therefore, I can write IC equal to HFE into IB. So once 1 by HOE is neglected, IC will become IC is equal to HFE into IB. IC is equal to HFE into IB. Let us say HFE into IB. Okay. Now, in the input circuit, from the input circuit, if you see the HIE, there is a voltage source, HRE into VCE. We will calculate the magnitude of this voltage source. How much is the voltage it is giving? So HRE into VCE is nothing but the output voltage. VCE is nothing but the output voltage across the load, right? See here, what is VCE? So VCE is nothing but the voltage across load. So I can write VCE as IL into RL. I will write VCE as IL into RL. So HRE IL into RL, HRE. If you see the collector current, this is IC. This is RL, IL, VCE. This is the output circuit part. IB. Instead of scrolling the pages up and down, I'm drawing wherever it is needed to whatever extent. So this is IC. So IC is now, this entire current is IC. So IC is nothing but HFE into IB. So VC I have written IL into RL. If I observe the current directions, I can write in place of IL minus IC minus IC into RL. So HRE IC is nothing but HFE into IB into RL. So minus HFE, HRE, IB, RL. So the magnitude of the voltage source HRE VCE is HFE into HRE into IB into RL. So whatever is the voltage coming from the source, that voltage is dropped across. That voltage is dropped across HIE, which is the voltage drop across HIE is drop across HIE. HIE is HIE into IB. Now, comparing the voltage across HIE and voltage of this source, then the HRE into VC, the voltage drop across HRE into VC, this source is very, very less compared with the drop across HIE. ఎందుకంటే హెచ్ఆర్ఏ ఉంది ఇక్కడ 10⁻⁻⁴ మైక్రో ఉంటుంది వాల్యూ. సో యూజింగ్ ద టిపికల్ వాల్యూస్ ఆఫ్ హెచ్ఎఫ్ఈ, ఇప్పుడు హెచ్ఆర్ఈ వాల్యూ క్యాలిక్యులేట్ చేయాలి అంటే మ్యాగ్నిట్యూడ్ ఆఫ్ ది వోల్టేజ్ సోర్స్ ఎలా వస్తుంది? హెచ్ఎఫ్ఈ సబ్స్టిట్యూట్ చేయండి, హెచ్ఆర్ఈ సబ్స్టిట్యూట్ చేయండి, ఆర్ఎల్ సబ్స్టిట్యూట్ చేయండి, ఇక్కడ కూడా హెచ్ఐఈ సబ్స్టిట్యూట్ చేయండి. సో ఇఫ్ యూ కంపేర్ జస్ట్ the voltage source, magnitude of this voltage source and the drop across this voltage across this HIE and voltage across the source. If you compare, this is going to be very, very negligible compared with drop across HIE. So this is going to be very less compared with the drop across HIE. We will see whether she has calculated or not. Okay, so just substituting HRE and HFE, product of 0.01 RL into IB, 0.01 RL into IB, so which is very, very small in comparison with the drop across this. So therefore, we can also neglect this source. This source can also be neglected. So neglecting the source means what? It is negligible. So almost zero. Therefore, we can replace this with short circuit. Now, this is the approximate model. So therefore, HRE into VCE can be neglected. Can be neglected. So now we are left with the two terms HIE, HFE. So these are the two terms, two H parameters which will be there in the approximate model. Approximate model. So just see here, HIE, this is the exact H parameter model.
మ్యామ్
Yes.
ఒకసారి పైన స్టెప్ రిపీట్ చేస్తారా మ్యామ్?
ఏంటమ్మా?
పైన స్టెప్స్ రిపీట్ చేస్తారా మ్యామ్ ఒకసారి? అండ్ నెగ్లెక్ట్ అయింది
చెప్తాను. ఇక్కడ చూడండి, ఇక్కడే రిపీట్ చేస్తున్నాను. We will connect a load resistor RL and we will connect a source VS. Internal resistance RS will be there. So this is IB, this is IC, this is IL, this is the collector, base, emitter. Okay. So ఒకవేళ if RL is very small comparison with this 1 by HOE, both comes in parallel, right? So these are in parallel, so very small, then the parallel combination of the two result into RL only. So parallel combination of the two result into RL, so we can neglect this 1 by HOE. And under that, if this 1 by HOE is removed, then the collector current IC will become HFE into IB. So this will not be there, and IC is same as HFE into IB. And if I calculate the magnitude of HRE into VCE, Atlanta HRE, VCE is nothing but the IL RL drop across, and HRE, IL is again minus IC into RL, and IC, after removing 1 by HOE, IC has become HFE into IB RL. Okay, so using the typical values of HRE, HFE, RL, if you calculate the magnitude of this voltage source, and if you compare the voltage across this source and voltage across this resistance, this is going to be negligibly small compared with this voltage across HIE. So source voltage, whatever the voltage we are getting, that will be divided among this input impedance HIE and the source. But source voltage is very, very less compared with HIE. Therefore, this we are neglecting. And this is the equivalent circuit. This is the equivalent circuit of approximate model. Now the same circuit I will modify. So this is the approximate model. RS and RL, anyhow, they will be the same, which are the externally connected components. So HI, HI is connected to the emitter like this. So what I'm doing, same circuit, I'm just redrawing in a different way. This is emitter terminal. To the emitter terminal, HFE is connected, current source, and this is collector. So this is collector, and this is the approximate model. ఇది approximate model. దీన్ని ఇంకొక రకంగా కూడా కనెక్ట్ చేయొచ్చు. HIE, HFE into IB. This is also the approximate model. Base, emitter, and collector. So the approximate model is derived from the condition that 1 by HOE from the condition that RL is very, very small. If this is satisfied, then only you can go ahead with approximate model. Otherwise, we have to use exact model only. First, you need to check this condition. RL 1 by HOE కంటే చాలా తక్కువ ఉంటేనే approximate model valid అవుతుంది. So the meaning is that HOE into RL So if this condition is satisfied, then approximate model is used. And you may think that this is the approximate model of CE, and if I replace I with C, I with C, HFC, IE, IB, you may think that this is the approximate model of CC. No, it is wrong. Approximate model is derived from the common emitter configuration only. From the common emitter configuration only. So if in the next class, how to analyze the common base amplifier, common emitter amplifier, and common collector amplifier using approximate model, approximate H parameter model. How to use using the approximate H parameter model? We will see in the tomorrow's class. So the same circuit we are going to use for we are going to use for the same circuit for CBCE CC amplifiers. For CBC, the emitter lid, collector, and base. Suppose common, just for example, I am showing common base amplifier. I have to form common base amplifier. So what I will do, the same circuit, I will rotate this circuit such that base terminal will come to the ground. Base will come to the ground. And input side emitter should come. Input side emitter should come. And output side collector. So like that you have to rearrange so the H parameters will remain as HIE and HFE only. Though we are analyzing common base, this will remain as HFE and HIE only. So this is the common base configuration. So in common base configuration, base will be grounded. So rotate this circuit, this lid, such that base will come down and connected to ground. Emitter will come to the input side and collector should come to the output side. Now, if you connect a source here and if you connect a load here, this is the equivalent circuit of the CB amplifier using approximate model. So the circuit is going to be same, whichever configuration we have to draw. That's if CC, collector terminal should come down and emitter come to the output side, like that. So this is the equivalent circuit of CB amplifier using approximate model. Using approximate model. Using approximate model. అదే కామన్ కలెక్టర్ అనుకోండి. కామన్ కలెక్టర్ అంటే కలెక్టర్ టెర్మినల్ గ్రౌండ్ అవుతుంది. కలెక్టర్ విల్ బి గ్రౌండ్. కలెక్టర్ షుడ్ కమ్ డౌన్. సో కామన్ కలెక్టర్లో ఇన్పుట్ ఏమొస్తుంది? బేస్. బేస్ కాబట్టి ఇది హెచ్ఐఏనే ఉంటుంది. హెచ్ఐఏ అండ్ ఎమిటర్. సో దిస్ ఇస్ ఎమిటర్ లైక్ దట్. The same circuit without changing the H parameters subscripts, we will use the same circuit. So this is for today. We will continue the analysis of amplifiers. Analysis means same, all current gain, voltage gain, input and output impedances we are going to find for all the three configurations using approximate model. So it is given in your syllabus, the analysis of CBCE CC using approximate model. So you need to know both exact and approximate model analysis. You can leave the class. CR, please send me the attendance.
Okay, ma'am.
Okay, you can leave class. I will upload notes now itself in another 5 minutes till whatever I have explained. Any doubts you can ask, otherwise I'll close the meeting. Any doubts? So in the 4th unit you will get a direct long answer question for 10 marks. Direct long answer. Comparison matram 5 marks question. CBCECC. Amplifier analysis will be direct 10 marks. సరే అయితే డౌట్లు ఏం లేవు అంటే కనుక నేను క్లోజ్ చేస్తాను.
Hello.
చెప్పండి.
What is the best amplifier among three amplifiers?